We're going to study now the Voyager mission, which is one of those interesting probes that were sent to space with a certain expectancy of just working for a few years, and thus kept going on and on. And today, 30 years after its launch, it's still working and sending interesting data to us. So let me state the problem we are going to study, and I propose you to go in detail. Here you have an image of the probe. It's in here. It's an artist's view, and it has different parts. But what is more visible is a 3.7 meter antenna that was needed to send the data to the Earth. A platform here with all the cameras, all the images, all the instruments that were taking images, different ones. Here you have two boom antennas for measuring the emissions mainly from Jupiter. It was the study of radio astronomy in some way. Since the probe could not be fed with light, with sunlight, it has to carry its own power supply. This is a 3-stage nuclear reactor. This is just the unit. And then on this boom, you don't see it, at the end is a magnetometer to measure magnetic fields. And below the antenna is really all the equipment, the fuel, and different plates with information. And one of them is this record with the sounds of Earth. And also there are messages, there are different images in there. And this is just the message that President Carter printed on the probe and was sent with the hope that maybe one day someone will find this probe somewhere in the universe. So this is just a brief description of the probes. There were two probes. They were just launched in 1977, and 2 years later they flew by Jupiter. Then they went to Saturn, and in principle that was the mission, but things were working, so they really pushed the mission to Neptune. And 10 years later they visited Neptune. The distance are written there. Jupiter was at 6.810 to the 8th, so 680 million kilometers, while at Jupiter it was 4,300 million kilometers. And they follow different trajectories. Only one of the probes went to Neptune. The other really went into space. Today they are leaving the solar system. The distance is rare. For Voyager 1 is 19.5 thousand million kilometers from the Sun, and it's heading north from the ecliptic plane, and is more or less traveling at 3.5 astronomical units per year, while the other is going southward, 48 degrees south of the ecliptic, and more or less at the same velocity. So both are really very far away, but they are still working and sending data to Earth. So we propose you to study those probes in detail and find the link budget, the signal-to-noise ratio. So this is the basic parameters you have here. The antenna is 3.7 meters in diameter, and it has a gain of 48 dBs at 8.4 gigahertz, which is the transmitting frequency from the probe to the Earth. And the power is 20 watts. It's less than a light bulb. So this is really the number to remember. And the signals are received by three large antennas located in California, Australia, and Spain. They are 120 degrees separation just to cover the whole Earth and receive from any point. At the time of the Jupiter encounter, the antennas had a diameter of 64 meters, a gain of 71 dBs, and a total system noise temperature of 28 Kelvin. They are really cryogenic receivers, and this is why you have such low levels of noise. For Neptune, the antenna size had to be increased to 70 meters. A couple of dBs were gained for the antenna gain there, and just 3 kelvins, they managed to lower 3 kelvins. But the images were sent from Jupiter at the rate of 150 kilobits per second, and from Neptune at 21.6 kilobits per second. But they had to change the bit rate. Now, we propose you to work the free-path loss for the Voyager 2 in those 2 encounters, and find the power received by the antenna. And you may account for some errors in there, atmospheric losses, up to 3 dBs, and check that this works. So this is a digital system. You need to know the modulation. What's a BPSK? What's a binary phase shift keying? And they require, for the images, a bit error rate of 5 × 10⁻³ And if you want to find the signal-to-noise ratio for this bit error probability, this will give you that for this case, under Gaussian white noise, this will give you a complementary error function of the energy per bit to noise power spectral density, which is just a complementary error function. And with this you can work those parameters. So find and check that the images could be received with this quality requirement from both Jupiter and Neptune.